Welcome, focused learners. If you've ever found yourself staring at a massive spreadsheet full of raw numbers, just kind of scratching your head and wondering how to find the hidden story inside all that data, well, you are absolutely in the right place. Today, in this explainer, we're embarking on a real data journey. We're going to tackle two of the absolute heaviest hitters in statistics, correlation and regression. We're going to figure out how to spot trends, measure relationships, and frankly, how to actually forecast the future using data. So grab your mental notebook and let's dive right in. To make all these abstract statistical concepts immediately practical, I want you to step into the shoes of an educator or an admissions counselor for a second. Just imagine you're sitting there staring at a stack of student files. You can see exactly how many hours each student studied for a massive exam, and right next to it, you see their final grade. Naturally, a question is going to pop into your head, right? Can you predict a student's grade based purely on their hours of study? Does one actually drive the other? This right here, this is the exact fundamental problem that correlation and regression were built to solve. Okay, let's look at some real numbers. Consider these 6 students, A through F. Student A studied for 6 hours and scored an 82%. Now compare that to student C, who studied for just a single hour and scored a 57%. But then check out student D, studied for 5 hours and totally knocked it out of the park with an 88%. Just scanning these numbers, your brain is probably already doing the math trying to find a pattern. You might assume, naturally, that more study hours lead to higher grades. But right now, that's really just a hunch. We need a concrete way to actually visualize this.
It's so funny, because human beings have such a drastic reaction to data trends. We see a line on a chart crash drastically, and our immediate instinct is panic, like we literally want to evacuate to the conference room directly below us. We just love jumping to massive conclusions the very second we see a trend pointing up or down. But hey, before we panic, we've got to learn how to properly construct and interpret these visualizations.
Section 1. Spotting the data trend.
So to find our trend, we use what's called a scatter plot. Now, our source material defines this as a statistical graph of two quantitative variables that provides a visual representation of their relationship. Think of it as our primary visual anchor. It's like a map. We take an independent variable, like the number of hours studied, which we'll call x because it's the factor that can be manipulated, and we map that on the horizontal axis. Then we take the dependent variable, the exam grade, which we'll call y because, well, we're assuming the grade depends on the study time, and we map that on the vertical axis. And just like that, those abstract, boring numbers become a clear map of dots showing us exactly how these two variables connect.
Section 2. Understanding correlation. Now, this is where the Pearson product moment correlation coefficient comes into play. We usually just represent this with the letter r. And r is a specific number that always falls somewhere between negative 1.0 and positive 1.0. If your r value is exactly 0, it basically means you're looking at a random, chaotic cloud of dots, absolutely zero relationship. No connection. But as that number creeps closer to those extremes, the relationship gets tighter. A positive 1.0 is a perfect positive relationship. As one variable goes up, the other goes up in absolute lockstep. A negative 1.0, that's a perfect inverse relationship. It's a true mirror image, so as one goes up, the other goes down in exact proportion.
To give this concept some real academic weight, our business research sources explain it like this. Covariance is the extent to which a change in one variable corresponds systematically to a change in another. Correlation can be thought of as a standardized covariance. I know, that sounds a bit dense. But in plain English, correlation is simply standardizing our data so we can easily understand both the magnitude, meaning exactly how strong the relationship is, and the direction, whether it's positive or negative. It literally just tells us if our two variables are systematically moving together.
Section 3. Interdependence versus dependence.
Okay, this brings us to the real thematic crux of this whole explainer. While correlation and regression are mathematically like cousins, they serve fundamentally different purposes. Correlation is an interdependence technique. That means it treats both variables as total equals, just observing to see if they associate like mirror images. It frankly doesn't care which one comes first. Regression, on the other hand, is a dependence technique. It makes a very strict, very firm distinction between an independent variable and a dependent one. Regression boldly stands up and says, variable x predicts variable y. It creates a strict, one-way, directional prediction.
Section 4. Predicting future outcomes with regression.
So, let's take off our educator hats for a minute and put on our business owner hats. Imagine we're looking at the price of Diet Cola on the horizontal x-axis and the resulting sales on the vertical y-axis. When we do this, a straight line cuts right through the middle of the dots. That right there is the famous line of best fit. Instead of just waving our hands and saying, oh yeah, price and sales are related, Regression analysis steps in and calculates the exact slope and angle of that line. It allows us to predict precisely how many sales we're going to lose for every single cent we raise that price.
But how does it actually draw that magic line? Well, it uses the regression equation. Y equals A plus BX. Simply put, Y is the prediction we're trying to find, and X is our known variable, like the price of that cola. Using a mathematical method called least squares, regression calculates the exact slope and the starting point. This ensures that the line drawn minimizes our prediction errors, mathematically forcing it to sit as perfectly close to all the actual data points as possible. It's pretty brilliant, honestly.
Section 5. The Golden Rule of Stats.
Now, here's the absolutely crucial point. Even a massive, undeniably strong correlation coefficient does not mean one thing actually caused the other. We absolutely have to avoid these common errors. First up, assuming causality. Look, just because ice cream sales and shark attacks go up at the exact same time doesn't mean eating ice cream literally causes shark attacks. Second, overlooking the third variable problem. In that ice cream and shark example, the hidden third variable is just summer heat. Everyone's at the beach. Third, having a restrictive range. If you only test professional athletes, you are completely missing the true picture of average human fitness. And finally, assessing a curvy linear relationship. Sometimes things go up, they hit a peak, and then they go back down, forming a curve. If you try to force a straight regression line through a curved relationship, your predictions are going to be completely, wildly wrong.
To protect ourselves from overstating our findings, which is so easy to do, statisticians use something called the coefficient of determination. You'll usually hear it called R squared. Actually, scratch the base correlation coefficient. R squared is a much better indicator of relationship strength. You get it simply by taking your correlation value, R, and squaring it. So why is this a game changer? Because it converts the relationship into a strict, easy-to-understand percentage. It tells you exactly what percentage of the variation in your dependent variable is directly attributable to your independent variable, leaving the rest of it to unknown outside factors. It's the ultimate reality check that keeps our predictions honest.
Which brings us to our final, parting thought. Data is just an incredibly powerful tool. Correlation allows us to see how variables reflect each other, kind of like a mirror. And regression? Well, it gives us the mathematical superpower to try and forecast the future, kind of like a crystal ball. But as we've seen today, they are absolutely not the same thing, and the math relies entirely on the human logic you apply to it. Data can absolutely show us the trend, but you've got to ask yourself, are you confusing the mirror with a crystal ball? Keep that in the back of your mind the next time you're staring at a spreadsheet full of raw numbers, eager to find the story inside. Thanks so much for joining me on this explainer, and keep learning.